Greetings and salutations, magical chemists. Let's talk about how equilibrium applies to electrochemistry. As you know, many chemical reactions are reversible, and we show this with a double-ended arrow. Well, it turns out the exchange of electrons in a redox reaction is reversible. Some quick reminders. Well, when we are at equilibrium, the rate of the forward and backward reactions is going to be equal. They're going to continue at the same rate, so the chemistry never stops. However, there is no net movement between reactants and products, which means there is no measurable voltage if an electrochemical cell has reached equilibrium. Now, a voltaic or galvanic cell, of course, is a battery. A voltaic or galvanic cell at equilibrium is a dead battery. As you know, we can write equilibrium constant K, which is the ratio of products to reactants, specifically at equilibrium. Now, for electrochemical cells, remember that pure solids and liquids are not included in your ratio of products to reactants, so that usually means only aqueous and occasionally gaseous things are going to be included in the product to reactant ratio. Since a galvanic or voltaic cell at equilibrium is a dead battery, it's honestly a lot more helpful to consider the ratio of products to reactants as Q when you are not at equilibrium, because it's when you're not at equilibrium that you actually have a voltage. Now, a galvanic cell by definition is spontaneous, which means it has a K value much greater than 1. Products are highly favored. However, Q is always going to be equal to 1 in a standard galvanic cell. That's because the concentration of your reactants and your products will be 1 molar. Since Q is still the ratio of products to reactants, your quotient, then 1 divided by 1 is going to give you 1. Doesn't even matter what the exponents are. That means since at equilibrium, the reaction is driven to produce lots of products, but currently you don't have that, this reaction will spontaneously make products, right? Definition of a galvanic cell. Now, of course, this is a redox reaction. That's why we're looking at them. So, in that process of making more products from the reactants, electrons are transferred, and that's why a current flows as the galvanic cell runs. Over time, as the reaction keeps running and you make more and more products, eventually you're going to reach the point where K equals Q. Well, when you've reached equilibrium and stability, you've got a dead battery. Which makes sense, right? Your battery's going to run until eventually it's dead. So if you look at that visually, okay, so comparing K versus Q. So this would be the preferred amount of products at equilibrium, but under standard conditions, right, you have less products than that. That's why it's going to spontaneously make products. So the voltage is going to flow. Remember writing alphabetically, so we're going from, as we go from reactants to products, our current is flowing because products are forming, and this is where your voltage is equal to the standard cell potential. The voltage is going to decrease as the system approaches equilibrium. We will talk more about that when we talk about the equilibrium at non-standard conditions. But the idea is the standard conditions, cell runs, voltage flows until K equals Q, and now you have a dead battery. In this unit, we're going to introduce a term that is super important for chemistry. It is called Gibbs free energy, or delta G. We are going to talk more about this next unit, but for now, you need to recognize that delta G is the change in free energy of a chemical system, which basically means a chemical system's ability to do work. In a spontaneous or thermodynamically favorable reaction, you will have a negative value of delta G. This, of course, is where we've talked about where you have a positive cell potential. This is where voltage is being created, where you have a battery. You might be thinking, that's weird. Why would you have a negative change in free energy? Well, the idea is that this is a system that will spontaneously do its thing. It's kind of like if you have a ball up on a slope, right? The ball up on a slope is going to spontaneously roll down to a lower state. So if you were measuring the change in height, just going to make up numbers. Let's say the ball was 10 meters up and it rolled downhill until it reached the bottom of the hill at 0 meters. So whenever you measure the change in something, it's always final minus initial. So it starts at a higher height, a higher energy, and it ends up at a lower height or lower energy. You are getting a negative answer. I was arbitrarily measuring meters because I was using this height, but we're actually measuring energy, units of energy. The key is, if you start at a higher potential energy and you go to a lower potential energy, you're basically releasing energy to the universe. And we show that release of energy as a negative sign. So this is known as an exergonic reaction, something that is thermodynamically favorable. An endergonic reaction is when you have a net positive Gibbs free energy. This is not spontaneous. It is not thermodynamically favorable, right? You can make a ball roll uphill. That's the thing. But the key part is there, you are making it. It's not going to spontaneously do it. So you could force the ball, if you push it, to go uphill, but it's not going to do it by itself. So this is a non-spontaneous process. This is what happens when you have an overall negative cell potential. You need some kind of external power source. Like you could use your hands to push a ball uphill, but we need a source of current to push the electrons uphill, metaphorically speaking, of course. Basically, not the direction that they want to go. Conceptually, that's what you need to understand about Gibbs free energy. But quantitatively, there are some fun equations that we get to introduce. The first equation, we chemists like to call the negative numph equation, because that's kind of what it looks like if you try to pronounce it. This shows the relationship between Gibbs free energy, delta G, and cell potential. If you know one of the two values, you can calculate the other. They're related by a couple of constants. N in this equation is going to be the number of moles of electrons transferred in a balanced redox reaction. That is key. And then there's this fun new constant called Faraday's constant. Faraday's constant is a kind of large number, 96,485 coulombs per mole of electron. It's a measurement of the charge transferred in 1 mole of electrons. And just like this equation, it is given to you on the formula chart. Now, we already know what cell potential is, standard cell potential, E naught. And E naught is, of course, measured in volts. What is very helpful in this equation as far as dimensional analysis is concerned is realizing that you can define a volt. It is joules per coulomb. So that's what allows the dimensional analysis to work on this. Okay, notes about units. Delta G is measured in kilojoules per mole. Sometimes joules per mole if it's small, but usually kilojoules per mole. So that's what you'll measure it on when we're practicing in class and when you're taking tests and quizzes, all that stuff. However, mastering chemistry uses the older units where the per mole is implied. So please make yourself a giant note here because this will mess you up if you don't remember. Okay, let's go ahead and take a look at how this equation works. Honestly, the trickiest part about this equation sometimes is calculating for N. Everything else is just plugging in the numbers. The key to successfully identifying N, or the number of moles of electrons transferred, is to think about the half reaction. So what I'll usually do is I will pick just one of the elements involved. Like, I don't know, nickel looks shiny, so I'm just going to consider the nickel 2+ going to solid nickel. Hopefully it's pretty clear at a glance. Okay, nickel 2+ needs to gain 2 electrons to turn into solid nickel. But don't forget about the multiplicative factors that you needed for the balanced equation. You had to multiply this whole thing times 3, and that's why your value of N is going to be 6. The units for this can get a little dicey. So it is 6 moles of electrons transferred per mole reaction. So that shows up in the units. Okay, you should go ahead and take a look at this second already balanced redox equation and calculate N. When you're ready to check, unpause the video. Did you get N equals to 2? Well, remember that you can pick either one of the half reactions. So for this one, I chose tin because I'm lazy, and tin didn't have any multiplicative coefficient. So it's just like, hey, solid tin going to tin 2 plus, lost 2 electrons. Boom, I'm done. Okay, hopefully now N makes sense. So let's go ahead and use the entire negative numph equation. Because number 2 asks us to calculate delta G naught in kilojoules per mole for a given reaction, and it gives you the standard cell potential in volts. It also wants to know if this reaction is thermodynamically favorable. You could answer that already, right? There's a positive cell potential. Yes, it's thermodynamically favorable. But we are going to answer in terms of delta G. Why? Because we can. My first step is to write down the equation and then start plugging stuff in. You're not actually required to write down the equation. However, a good number of people, the biggest mistake is they forget that negative. So I do find it helpful myself to go ahead and write down the equation first. But now we can go ahead and start plugging things in. This balanced reaction is pretty straightforward, right? Everything's going from either neutral to +2 or +2 to neutral. So hopefully you can see that N equals 2. And then, in case you forgot what the F was, well, it's Faraday's constant, and it is a constant that is given to you on the formula chart. And then, of course, E naught cell, they actually told you that. It was 0.79 volts. Now, you might recall that we're looking for delta G in kilojoules per mole reaction. Well, these units don't seem like they cancel out. Okay, moles of electrons is on the top and the bottom, so that one can cancel. But I've got coulombs and volts. Oops. And so right now, I do have the per mole of reaction. This is where recognizing that volts can be rewritten will help your dimensional analysis. You don't have to rewrite it, but it can help you see the units. Volts are actually joules per coulomb. One of the reasons this is so helpful, because now you'll notice, hey, look, coulombs cancel. You are spitting out an answer when you just plug in terms of volts. You're not getting an answer in kilojoules per mole reaction. Your number is in joules per mole reaction. And sig figs are still a thing. Please note you are not using the number 2 for sig figs. That's because it's considered a whole number, a counting number. It's exactly 2 moles of electrons. However, your cell potential is totally counted for sig figs. So we get to keep 2 sig figs. So rounding for sig figs, I get negative 150,000 joules per mole reaction, but they wanted the answer in kilojoules per mole reaction. So that is a quick fix. Hopefully you remember that there are 1,000 joules in 1 kilojoule. So our final answer to this lovely and delicious problem is negative 150 kilojoules per mole reaction. Don't forget, they also asked you, is this reaction thermodynamically favorable? This is going to be one of the easiest free response questions to answer because you have a negative delta G value. By definition, it's thermodynamically favored. Okay, so that's the negative numph equation. I am sure you are excited to know that there is actually another equation we can use with delta G. This is a fun one. We call it negative ratlink because, well, this isn't the reason because, we just call it ratlink because that's kind of what it looks like, but this relates delta G and the equilibrium constant K at standard conditions, which means 1 molar, 1 atmosphere, and 298 K. Notice, not 273 K. This is not standard temperature and pressure. Standard conditions for electrochemical cells are 25 degrees Celsius, which is room temperature, which honestly kind of makes sense. Now the R in ratlink, of course, R, it's a pirate's favorite constant, the universal gas constant. But now we are going to be working with the energy R, the one that we have not been using for PivNert, 8.314 joules per mole. Joules per mole Kelvin. That's how you read all those negative exponents. Your temperature, of course, must be in Kelvin, and K is the equilibrium constant. Ln is the natural log base E. If you don't know what that means, that is totally okay. For our purposes, the natural log is going to be a button on the calculator. Now this equation is just a teensy bit more mathematically complicated than negative num. Because if they give you k, the equilibrium constant, you can just plug in, use the button on your calculator, natural log of k times negative r times t, blah, blah, blah. You'll get delta g. However, if they give you delta g and want you to solve for k, you have to rearrange this equation to solve for k. Now, if logarithms make sense to you, this is going to be a relatively easy thing to undo the natural log. A natural log is just the inverse of the exponent. If that sounds like gibberish, you might want to memorize the following equation, because the equation below is just a rearranged version to show you how to solve for k. If you can't derive it, you have to memorize it. When you calculate delta G using the negative Ratlink equation, it is going to spit out your answer in joules per mole reaction. Remember, most of the time, if you're solving for delta G, they will ask you for kilojoules per mole reaction. So make sure you're aware the equation as written will calculate joules per mole reaction. Of course, mastering chemistry here would just use joules, because the per mole reaction is implied for mastering chem. Okay, so here is a brief little summary table that kind of shows you the cell potential, delta G, and K all in one place. Things that are thermodynamically favorable. Well, they have a K greater than 1, right? They're spontaneously making products to reach equilibrium. As we know, that means their standard cell potential is positive, and as we now know, that means delta G is negative. E naught cell and delta G will always have the opposite signs. It's because of the negative num equation, of course. A reaction that is not spontaneous or not thermodynamically favored means at equilibrium, of course, doesn't want to make products, it wants to stay with its reactants. So it has a negative cell potential. It's not going to do it unless you make it, which is a positive delta G. You have to push that ball up a hill. You have to push those electrons away from the direction they want to go. And if you're at equilibrium, you're just kind of a dead battery. You have no cell potential, you have no delta G, and your K, well, actually your K shouldn't be equal to 1, so that should be K equal to Q. Oops, let's fix that. And because that is, of course, a dead battery, I'm going to keep drawing my creepy skull face. Okay, let's go ahead and try one practice problem that pulls both of these beautiful equations together. Yum. In this problem, they've given you a balanced redox reaction. That's a loud bell. And they gave you the standard cell potential. And the first thing it says is calculate the free energy change. Now, you have to recognize that when they say free energy change, that means delta G. And they are asking you to calculate it in kilojoules per mole reaction. Well, hey, we've actually already done this. So I think you should try this delicious problem. Go ahead and pause the video. And when you're ready to check your answer, or you just need a little help, unpause the video. Okay, hopefully you realized that if you're given the standard cell potential and you need delta G, you're just plugging into the negative num equation. The balanced chemical equation allows you to determine that N is equal to 2. Now you could do that by looking at the change from S4062- to S2032-, but why would you do that when you could just look at the change in chromium? Each chromium loses 1 electron, but it has a multiplicative factor of 2. So that's how I got in. Of course, Faraday's constant is a constant, and then they gave you the standard cell potential. You are not required to write the units here. However, they will help you remember that your final answer is not kilojoules per mole. With 2 sig figs, that gives us negative 130,000 joules per mole reaction, which we can then convert to kilojoules per mole reaction. Be careful about skipping steps here. If you just did this, you're like, okay, I plugged into my negative num, and you just wrote, yeah, when I plug that in, that equals negative 130 kilojoules per mole reaction. Nope, you would not get the point. Because mathematically, that's not true. You have to show somewhere that you're taking that dividing by 1,000. So you could slap a divided by 1,000 there, and then you could do that. But you have to make sure you're not writing a lie, because then we can't give you full credit even though we knew exactly what you were doing. Okay. There is a second part to this problem. It says, okay, that's great. So let's calculate the equilibrium constant, which of course is K. Hopefully you remember that once we know delta G, you can connect to K through the negative Ratlink equation. There we go. When solving for K, I have found it more straightforward to do this in 2 steps. First, I rearrange to get the natural log of K all by itself on one side, and I like to go ahead and plug it and solve for that. So let's plug in our values. Watch out for units. Honestly, it is the units that tend to trip people up the most on these problems. Remember that we are using the energy R value. And energy R, that 8.314, is in terms of joules per mole Kelvin, which means you would need to use delta G in terms of joules per mole reaction. I have seen some students who will take this value and they will convert it to kilojoules per mole Kelvin, right? You just divide by 1,000 and you can do that. However, just make sure you need to make the units for delta G and R match. Because again, this is where people, if they're skipping steps, not writing down units, this is where the points get lost. Notice that the negative delta G cancels out the actual negative from our value. So once we plug all this stuff in together, we get a overall positive value for the natural log of K. There are more numbers here, but I didn't write down everything in my calculator. I just used that when I was doing the answer. Because now, if the natural log of K is 52.47, to undo the natural log, I have to take e raised to the power of. I know you're probably thinking, but Lestic, you said I didn't have to understand the natural log. You don't, because if you look at your calculator, so you find the natural log, the ln button, e to the power of is basically second ln. So that's all you have to remember. To undo natural log, do second natural log, and it'll be e to the power of. And hopefully you can realize this is going to be a big number. It makes sense that K is a lot greater than 1. We've got a positive cell potential. This is thermodynamically favorable. Okay, so those 2 equations will get you through everything you need to know about electrochemical equilibrium at standard conditions. So thank you for playing with the glories of chemistry.